Hey guys, thanks for tuning in. This is part 2 of my video about vectors, and I'm going to start by talking about how to recognize when a pair of lines in three-dimensional space are perpendicular to each other. So what I have here are two lines that are defined parametrically. I have my L of t and M of t here, and I want to figure out, do these lines cross each other at a 90-degree angle in three-dimensional space? And this is a two-step process. Step 1 is make sure the lines actually intersect with each other. That's a given in two-dimensional space, but in three-dimensional space, other interesting things can happen that we'll talk about soon. So the first thing that we notice is that L of 0 is equal to M of 0, which is equal to 1, 4, 2. So we found an intersection point between our two lines. And then the next thing that we do is we go ahead and say that we have the vector 3, 1, 1 and the vector 0, negative 1, 1. We're going to take the dot product of these two slope vectors, and if this dot product comes out to 0, which it will, these two facts together are enough information to say that L of t and M of t are perpendicular. You need the two lines to actually intersect each other, and you need the dot product of their slope vectors to equal 0. Now for our next example, I have a similar pair of lines, but I've got a slightly modified L of t and M of t. What you could see here is that the starting points for L of t and M of t have been shifted a little bit, but by the way, these slope vectors are going to remain the same. It's not enough to just say, oh, the dot product of 3, 1, 1 and 0, negative 1, 1 is equal to 0, so therefore the lines are perpendicular. Nope, we have to do a little bit more work here, and that little bit of extra work is to determine whether these two lines actually have an intersection. Now sometimes you can eyeball it, so if you're ever able to just look at this and see the answer, go for it. Like for this particular example, if you take your L of t here, I could see that L of 1 would equal 2, 0, negative 1 plus 3, 1, 1, which is going to equal 5, 1, 0. Oh, I just found it. The intersection point between L of t and M of t is the point 5, 1, 0, because I know that M of 0 is equal to L of 1, and there's our intersection point. That's enough to prove that our lines actually intersect each other. And that the lines are perpendicular. We have our intersection at 5, 1, 0. We have the dot product of 0 between our two slope vectors. That proves the lines are perpendicular. Now, if you ever get stuck and you can't find it, just eyeballing the equations is often successful for small, easy to find intersection points. But if you need to do something more complicated, just solve the system of equations that you get when you set L of t equal to M of s. Intersections between parametric curves. These two curves need to be at the same point in space, possibly at different times, in order for there to be an intersection. So you can always solve that system if you need to. In this example, we're going to see an instance of two lines that at first glance look like they might be perpendicular to each other, because again, we see these two slope vectors of 3, 1, 1 and 0, negative 1, 1, and we take this dot product and we get 0. So you might think, oh, for sure these two lines are going to be perpendicular to each other because their slope vectors are perpendicular to each other. The dot product of their slope vectors is 0. And even if you look from a particular angle, you might say, yep, those two lines are intersecting at a 90-degree angle. But if you kind of change the camera angle just the littlest bit, you'll notice that actually the vectors themselves might be perpendicular, but the lines are skew. And the way that we can determine this algebraically is to solve the system of equations L of t is equal to M of s. And what we want to determine is whether these two lines actually intersect each other. So you could go ahead and unpack this and say 5, 1, 0 plus, this gets a little bit ugly just because there's so much going on here algebraically. We have a bunch of ordered triples. But the actual mathematics behind solving this system, nothing more complicated than things that you guys did in Algebra 2. So you set up the equation like that. Now we're going to thread everything out. We're going to thread apart into an x of t, a y of t, and a z of t. So I'm going to get 5 plus 3t from the left-hand side, I can highlight here to show you 5 plus 3t is equal to, and then from the right side of the equation, I'm going to thread out these x coordinates, negative 3 plus 0s. And we're going to do that for each of the x and y and z coordinates. So then we thread out the corresponding y coordinates, and you would get 1 plus 1t is equal to 1 minus s, and so on and so forth. We're going to do it for the z coordinate as well. 0 plus 1t is equal to 2 plus 1s. Now that's a system of equations, and if you go ahead and solve that system, you're going to get no solution. I'm not going to go through and do elimination or substitution for you, but you guys can check that on your own. You could also run it through Mathematica, and Mathematica will very quickly give you the empty set as your solution, as in those two lines do not intersect each other. And if the two lines don't intersect, it doesn't even matter that the dot product between these slope vectors is 0. The lines are skew, and so there's no perpendicularity you could ever find anyway. So actually, it's probably a better idea to check for intersection first and not really worry about the dot product between those vectors until later, because if the lines don't intersect at all, perpendicularity is pointless anyway. And for parallel, so we have a new L of t and M of t here, and what you'll notice is that we have the same slope vector for both of these lines. And so you might say, oh yeah, guaranteed that these are parallel to each other. And maybe they are, maybe they aren't. We have to do a little bit more work to figure that out, because what we care about is whether these two lines share any points in common. There's basically two different scenarios that can happen when you have lines that have the same slope. Either you could have two lines with the same slope and they don't share any points in common. Those are called parallel lines. But if you're not careful, you might not notice when you actually get the same line twice. If it happens to be that you have some points on one line that shows up on the other line, you don't have two parallel lines, but the same line kind of overlapping itself. And so we want to make sure that we check for that. Now, one nice thing about parallel lines is if you have two lines that have the same slope, and you can see we share the same slope vector here, these two lines are either going to share all of their points in common or none of their points in common. And so the easiest thing to do is just pick one point from one of the lines. I'm going to arbitrarily pick 1, 4, 2, but there's infinitely many choices here. And I'm going to try to figure out, is 1, 4, 2 on M of t? Is there a t value at which M of t reaches the point 1, 4, 2? If there is, then we don't have parallel lines. We have the same exact line twice, the same locus of points traced out in space. And if this has no solution, then we have parallel lines. We have what we actually wanted. And again, you could thread this out into a little system. So you can write 1 equals 5 plus 3t, 4 equals 9 plus 1t, 2 equals 6 plus 1t. And if you solve this little system here, you're going to get some sort of inconsistency. You're going to get some sort of no solution going on. This one's really quick. I can just show you what happens. You would get 3t is equal to negative 4. So t is equal to negative 4/3. For the next equation, you would get negative 5 is equal to t. And for the last equation, you would get negative 4 is equal to t. Well, this is supposed to be a simultaneous set of equations here. Basically, we're supposed to find a t value that satisfies all three equations at once. We just got 3 different answers. So this is not going to happen. So the point 1, 4, 2 is not on the line M of t, which means we have the same slope vector. They don't share any points in common, because if they don't share this one point in common, these two lines are not going to share any of their points in common since they have parallel slope vectors. So we've verified that we have. Here's another one. I've kept the slope vectors the same, but I've changed my starting points up a little bit. And in this case, you actually do get that these are the same line twice. Now, if you want to eyeball it instead of solving a system, occasionally you might look at one of these equations and say, oh, look at this. If I calculate m of 1, that's negative 231 plus 311. And when I add that all together, I get 142. Oh, that's the starting point for L of t. So I now know that L of 0 is equal to m of 1. They share a point in common, but since they have the same slope vector, they don't share just a point in common, they share all of their points in common. These are not parallel lines. This is the same line twice. Finally, in this example, we have two lines that look like they're very different from each other. You might glance at these and say, oh, for sure these are just unrelated lines. They're not parallel because they have different slope vectors, different starting points, and so these are just two completely different lines with no relationship to each other. Parametric equations aren't that simple though, because if you take this slope vector of 311 and this slope vector of 622, you might notice that there is a relationship here. If I double 311, I get 622. These two slope vectors point in the same direction, even though they're not exactly the same vector. These vectors are scalar multiples of each other. It's very similar to the concept that you might have run into when you were first learning Algebra 1. When you were in Algebra 1, you might have a line with a slope of 3/5 and another line with a slope of 6/10, and a beginner who's just looking at Algebra 1 for the first time might say, oh, these two lines have different slopes, so those two lines have no relationship to each other because the slopes are different. Except, you guys already know that 6/10 reduces to 3/5. And so actually these slopes are equivalent. Those slopes are describing parallel lines. Same idea here. Even though we have two different looking slope vectors, if one vector is a scalar multiple of the other vector, that means that those slope vectors are going to be parallel to each other. Now, of course, that's not a guarantee that the lines are parallel to each other. We just know that the slope vectors that generate those lines are parallel. Now we need to check either these lines share all of their points in common or none of their points in common. And we either have parallel lines or the same line twice. We need to do some algebra to try to figure it out. Now you could try solving a system like we've looked at before. You could easily do something like L of t is equal to m of s, solve that system, and if you get a true statement or some sort of algebraic relation, that would be an indication that you have the same line twice, and if you get no solution, that would be an indication that you have parallel lines. But honestly, if you can eyeball it, do it. When I look at this L of t right here, the first thing that comes to mind is that if I have L of 3, that's 142 plus 3 times 311, which is 142 plus 933. And that 933 plus that 142, you can already see where this is going. I'm going to get 1075. Oh, so L of 3 is equal to m of 0. I just got lucky there that these were simple enough equations that I can kind of figure it out in my head and I didn't have to solve a system. But I know that I have parallel slope vectors, and I know that my two lines share a point in common. That's going to imply that they share all of their points in common. These are not parallel lines. It's the same line twice. They look very different, but they are the exact same lines in space. All right, transitioning here, guys, I'm going to talk a little bit about unit vectors and a little bit about velocity vectors. You might remember this from your physics courses or your Trig Calc A course. If I have a parametric path, x of t, y of t equals, say, t squared, comma, 5t minus t squared. There it is on the screen in blue here. You can see this parametric plot. If I want to compute the tangent vector at x equals 1, or the velocity vector at t equals 1, here's how you do it. First of all, we're going to take the derivative. So we have f prime of t is equal to 2t, comma, 5 minus 2t, just the derivative of t squared, comma, the derivative of 5t minus t squared. And at t equals 1, I get the vector 2, comma, 3. That's the tangent vector or the velocity vector at time t equals 1. Now, if I want to plot that vector 2, comma, 3, I better figure out where on that curve I should be putting the vector 2, 3. So the tail of that curve is going to be at f of 1, the position of the particle at time 1, which is 1, 4. So I'm going to go to the point 1, 4 on the curve, and then I'm going to plot the vector 2, 3. And you guys can see right here, this vector goes right 2 and up 3 to make that happen. And it looks like a tangent vector to that curve. Now the unit tangent vector is that same exact vector, but I'm going to scale it down so that its magnitude is equal to 1. It's also called a direction vector. So the way we compute that, and this always works, a unit vector is we take our original vector and divide it by its own magnitude. We basically take a vector and divide out its magnitude information, and what we're left with, the reason they call it a direction vector, is all we have left is direction information. We know the direction of that tangent vector or the direction of that velocity vector, but without the distraction of its magnitude. And the reason this is useful for people is, especially in a physics context, there are certain situations where you care about the direction something is traveling in, but you don't necessarily care about, the velocity or the speed at which it's traveling. We just care what is the bearing of this? What direction is this particle traveling in? And what can get confusing is if two different people are doing the calculations and they don't turn them into unit vectors at the end, they might have the same answer but off by a scalar, in which case they might not realize that their vectors are pointing in the same direction. So this is a nice way to standardize or normalize a vector by writing in its unit tangent version, in its unit vector version. So quick definition here. A vector of length or magnitude 1 is called a unit vector. And so you would always say that the magnitude of a unit vector is equal to 1. Cool little fact here, when you guys learned about the unit circle in Trig Calc A, the unit circle actually parameterizes the full set of every unit vector on the planet. The unit circle gives you all possible unit vectors that could possibly exist in two-dimensional space. There's a little proof of that. You guys can read that on your own if you find it interesting, but it's kind of neat to see how all of the different mathematics you guys have learned over the years kind of tie together. When you were learning the unit circle, you weren't thinking about vectors, but in a sense, you were actually learning about vectors. Just a little summary here. You already saw this information on the previous slide, but if you ever need a unit vector, take your vector v, divide it by its own magnitude, and that should give you a unit vector. And sometimes you'll hear that called normalizing that vector. It's a way of taking your vector and stripping out its magnitude information and just leaving behind information. And finally, let's kind of continue with this physics idea. Let's say that we have a particle traveling along an ellipse. In this case, P of t is equal to 8 cosine t, 3 sine t. So maybe it's like a charged particle going through a magnetic field or something. There's all sorts of different contexts that you can imagine something traveling in an ellipse. But if we compute the velocity vector, our v of t is just p prime of t. We take the derivative of 8 cosine t, we get negative 8 sine t. We take the derivative of 3 sine t and get 3 cosine t. We could also compute the acceleration at any given point or at any given time. So the acceleration vector is the second derivative of p of t. Just take one more derivative, negative 8 cosine t, one more derivative, negative 3 sine of t. Now we could start plotting some of that information. So we could plot the velocity and acceleration vectors at t equals 0 seconds. All you do is you plug 0 into p of t to get your starting point, and then plug 0 into v of t and a of t, and that'll give you the velocity vector and the acceleration vector that should be starting at p of 0. In this case, 8, 0 is where we're starting. We could keep adding more, right? So we have at t equals pi over 6 seconds, you do the same thing, just a lot of plugging in and plotting, so on and so forth. Again, we could see the velocity vector and the acceleration vector as our particle moves along this curve. I'm just going to press forward a few times so we get a more full picture. So why do we care about this? Well, what we end up getting is we could figure out the position of our particle at any given time, and we could figure out the velocity and the acceleration from this plot. So we know the direction that this particle is traveling in. It's going in the counterclockwise direction. And then, this might be reminiscent of a physics class because we could see that the acceleration is always in towards the center here. Be careful, this is not a circular path, so the angle between the velocity vector and the acceleration vector is not guaranteed to be 90 degrees. When you guys were in physics and you had circular trajectories, you did expect the velocity and acceleration to always be perpendicular to each other. That is not the case in general. In fact, for this ellipse, it's only true 4 times along the coordinate axes, actually. And for the rest of the ellipse, the angle between those vectors is either acute or obtuse, but not 90 degrees most of the time. So what would someone use these velocity vectors for? We often use them in this class to figure out the orientation of a curve, or in a physics context, what direction is this particle traveling in? And you could always figure out its speed from the magnitude as well. So some things that we could see here, the particle is moving pretty slowly at this initial point, and look at how the magnitude of these vectors is getting longer until right here, that's a pretty large magnitude. So this basically this particle is going slow around the tight curve, and then on the straightaway it's speeding up, and then when it gets to the next curve it's slowing down, and then on the straightaway it speeds up. You could figure out, you could almost trace it with your finger, the speed of that particle as it moves along that curve. Slow at those tight curves and fast along those straightaways. Now, you don't want to get fingerprints on your computer every single time you do a problem like this, and so we do have another option for trying to track the speed of our particle over time. Remember, I said that the particle was going to be going slow around the curve and fast along the straightaway, and then slow along the tight curve and then fast on the straightaway. Well, algebraically, the way that we come up with a plot of the speed of this particle versus time is we plot the magnitude of the velocity vector, in this case just letting t go from 0 to 2 pi, since that was one full loop around our ellipse. And how do we get the magnitude of the velocity vector? Well, be careful here, this is not absolute value. So I have had countless students over the years say, oh, well, this is -8 sine of t, comma 3 cosine of t, and these look like absolute value bars to me, so I guess I don't know, I guess absolute values make a negative into a positive, so this is just the vector 8 sine of t, comma 3 cosine of t, or something like that. That's not going to work, guys. These are not absolute value bars, this is magnitude. And one way that you could tell that what I just tried is not going to work is magnitude is going to give us a scalar. And so we need some way of converting a vector quantity into a scalar. Well, we learned this in the previous slideshow. It's dot products, right? There's going to be a dot product in this. So this is the square root of the dot product of v of t with itself. And when we take that dot product, that's going to be a scalar. Now you could actually go ahead and compute an entire formula for that if you wanted to. So that's going to be the square root of 64 sine squared of t plus 9 cosine squared of t. And that's what this plot is. It's a plot of that function. And what does that function tell us? Well, again, it tells us when the speed of this particle is going faster or slower. This is not a parametric curve. This is a scalar plot, where if you were to label the y-axis, it would be speed. And if you were to label the x-axis, it would be time. This is speed versus time. It's not a parametric curve. It's just a plot of, hey, at time t equals 0, our particle's going pretty slow. At time pi over 2, our particle's going really fast. And then at pi, it's going slow again, and then fast, and then slow. Which you guys were able to see on that previous slide with the ellipse. When we were tracing it out, we saw that the particle was going slow around the corner and then speeding up at the straightaway, and then slow around the corner, speeding up along the straightaway, so on and so forth, which you could see happening in that plot. And if we compare everything side by side, we can kind of match it all up together. If we want to understand our scalar plot, we understand our scalar plot by looking at the magnitudes in our vector plot here. So you could see that this slower speed corresponds to this smaller magnitude. This larger magnitude matches up with this higher speed, and so on and so forth. And then remember, guys, that the acceleration vectors are pointing inward, because if you imagine that you were kind of spinning maybe you put a tennis ball on a string and you're spinning that string. If you were to cut that string while you were spinning it, the ball would fly off in the direction of its velocity vector. So we need that acceleration inward to keep that particle on the track. And then remember, if the particle suddenly fell off the track, or if you cut the string on that tennis ball, whatever object you're thinking about, that particle, that tennis ball, whatever, that train would continue going in the direction of the velocity vector. The velocity vector is going to tell you where that object would go if it suddenly was no longer held onto the track that it was traversing as it went on in that loop. And then remember, the velocity and acceleration vectors are not always perpendicular. Here's an easy proof of it. Take the dot product of v of t and a of t, and if that formula does not reduce to something that is always equal to 0, which it's not going to reduce to that, then those vectors are not always perpendicular. In terms of when they are and aren't, I'll let you guys find those, but I already mentioned it. At those coordinate axes are the only times that we're going to end up with velocity and acceleration being perpendicular, at least on this ellipse. Anyway, guys, make sure you're reading the basics and tutorials. There's a lot more information in there than I'm able to include in these lectures. This is not a lecture-based course, and so unfortunately I can't do an hour lecture every single day to cover everything. So certain topics that I wasn't able to cover in these 2 lectures, you'll be able to find those if you look at the basics and tutorials in CASIL.